In statistics, an estimator is a rule for calculating an estimate of a given quantity based on observed data. Thus the rule, the quantity of interest and its result are distinguished. There are point and interval estimators. The point estimators yield single-valued results, although this includes the possibility of single vector-valued results and results that can be expressed as a single function. This is in contrast to an interval estimator, where the result would be a range of plausible values. Estimation theory is concerned with the properties of estimators, that is, with defining properties that can be used to compare different estimators for the same quantity, based on the same data. Such properties can be used to determine the best rules to use under given circumstances. However, in robust statistics, statistical theory goes on to consider the balance between having good properties, if tightly defined assumptions hold, and having less good properties that hold under wider conditions. Background. An estimator, or point estimate, is a statistic that is used to infer the value of an unknown parameter in a statistical model. The parameter being estimated is sometimes called the estimand. It can be either finite-dimensional, or infinite-dimensional. If the parameter is denoted theta, then the estimator is traditionally written by adding a circumflex over the symbol. Sometimes the words estimator and estimate are used interchangeably. The definition places virtually no restrictions on which functions of the data can be called the estimators. The attractiveness of different estimators can be judged by looking at their properties, such as unbiasedness, mean square error, consistency, asymptotic distribution, etc. The construction and comparison of estimators are the subjects of the estimation theory. In the context of decision theory, an estimator is a type of decision rule, and its performance may be evaluated through the use of loss functions. When the word estimator is used without a qualifier, it usually refers to point estimation. The estimate in this case is a single point in the parameter space. Other types of estimators also exist. Interval estimators, where the estimates are subsets of the parameter space. The problem of density estimation arises in two applications. Firstly, in estimating the probability density functions of random variables, and secondly in estimating the spectral density function of a time series. In these problems, the estimates are functions that can be thought of as point estimates in an infinite-dimensional space, and there are corresponding interval estimation problems. Definition. Suppose there is a fixed parameter that needs to be estimated. Then an estimator is a function that maps the sample space to a set of sample estimates. An estimator of is usually denoted by the symbol. It is often convenient to express the theory using the algebra of random variables. The estimate for a particular observed dataset is n, which is a fixed value. Often an abbreviated notation is used in which is interpreted directly as a random variable, but this can cause confusion. Quantified properties. The following definitions and attributes are relevant. Error for a given sample. The error of the estimator is defined as where is the parameter being estimated. Note that the error, E, depends not only on the estimator, but also on the sample. Mean squared error. The mean squared error of is defined as the expected value of the squared errors, that is, it is used to indicate how far, on average, the collection of estimates are from the single parameter being estimated. Consider the following analogy. Suppose the parameter is the bull's eye of a target, the estimator is the process of shooting arrows at the target, and the individual arrows are estimates. Then high MSE means the average distance of the arrows from the bull's eye is high, and low MSE means the average distance from the bull's eye is low. The arrows may or may not be clustered. For example, even if all arrows hit the same point, yet grossly miss the target, the MSE is still relatively large. Note, however, that if the MSE is relatively low, then the arrows are likely more highly clustered. Sampling deviation for a given sample. The sampling deviation of the estimator is defined as where is the expected value of the estimator. Note that the sampling deviation, d, depends not only on the estimator, but on the sample. Variance. The variance of is simply the expected value of the squared sampling deviations, that is, it is used to indicate how far, on average, the collection of estimates are from the expected value of the estimates. Note the difference between MSE and variance. If the parameter is the bullseye of a target, and the arrows are estimates, then a relatively high variance means the arrows are dispersed, and a relatively low variance means the arrows are clustered. Some things to note. Even if the variance is low, the cluster of arrows may still be far off target, and even if the variance is high, the diffuse collection of arrows may still be unbiased. Finally, note that even if all arrows grossly miss the target, if they nevertheless all hit the same point, the variance is zero. Bias. The bias of is defined as it is the distance between the average of the collection of estimates, and the single parameter being estimated. Note that the bias of is a function of the true value of, so saying that the bias of is means that for every the bias of is, the bias also is the expected value of the error, since, if the parameter is the bullseye of a target, and the arrows are estimates, then a relatively high absolute value for the bias means the average position of the arrows is off target, and a relatively low absolute bias means the average position of the arrows is on target. They may be dispersed, or may be clustered. The relationship between bias and variance is analogous to the relationship between accuracy and precision. The estimator is an unbiased estimator of if and only if. Note that bias is a property of the estimator, not of the estimate. Often, people refer to a biased estimate or an unbiased estimate, but they really are talking about an estimate from a biased estimator, or an estimate from an unbiased estimator. Also, people often confuse the error of a single estimate with the bias of an estimator. Just because the error for one estimate is large, does not mean the estimator is biased. In fact, even if all estimates have astronomical absolute values for their errors, if the expected value of the error is zero, the estimator is unbiased. Also, just because an estimator is biased, does not preclude the error of an estimate from being zero. The ideal situation, of course, is to have an unbiased estimator with low variance, and also try to limit the number of samples where the error is extreme. Yet unbiasedness is not essential. Often, if just a little bias is permitted, then an estimator can be found with lower MSE or fewer outlier sample estimates. An alternative to the version of unbiased above is median unbiased, where the median of the distribution of estimates agrees with the true value. Thus, in the long run, half the estimates will be too low and half too high. While this applies immediately only to scalar-valued estimators, it can be extended to any measure of central tendency of a distribution. See median unbiased estimators. Relationships among the quantities the MSE, variance, and bias, are related, i.e., mean squared error equals variance plus square of bias. In particular, for an unbiased estimator, the variance equals the MSE, the standard deviation of an estimator of theta, or an estimate of the standard deviation of an estimator of theta, is called the standard error of theta. Behavioral properties. Consistency. A consistent sequence of estimators is a sequence of estimators that converge in probability to the quantity being estimated as the index grows without bound. In other words, increasing the sample size increases the probability of the estimator being close to the population parameter. Mathematically, a sequence of estimators, Tennessee, n0, is a consistent estimator for parameter theta if and only if, for all greater than 0, no matter how small. We have the consistency defined above may be called weak consistency. The sequence is strongly consistent, if it converges almost surely to the true value. An estimator that converges to a multiple of a parameter can be made into a consistent estimator by multiplying the estimator by a scale factor, namely the true value divided by the asymptotic value of the estimator. This occurs frequently in estimation of scale parameters by measures of statistical dispersion. Asymptotic normality. An asymptotically normal estimator is a consistent estimator whose distribution around the true parameter theta approaches a normal distribution, with standard deviation shrinking in proportion to as the sample size n grows. Using to denote convergence in distribution, Tennessee is asymptotically normal if for some v. In this formulation v, n can be called the asymptotic variance of the estimator. However, some authors also call v the asymptotic variance. Note that convergence will not necessarily have occurred for any finite n. Therefore this value is only an approximation to the true variance of the estimator, while in the limit the asymptotic variance is simply zero. Stated a little more accurately, the distribution of the estimator Tennessee converges weakly to a Dirac delta function centered it. The central limit theorem implies asymptotic normality of the sample mean as an estimator of the true mean. More generally, maximum likelihood estimators are asymptotically normal under fairly weak regularity conditions. See the asymptotics section of the maximum likelihood article. However, not all estimators are asymptotically normal. The simplest examples are found when the true value of a parameter lies on the boundary of the allowable parameter region. Efficiency. Two naturally desirable properties of estimators are for them to be unbiased and have minimal mean squared error. These cannot in general both be satisfied simultaneously. A biased estimator may have lower mean squared error than any unbiased estimator. See estimator bias. Among unbiased estimators, there often exists one with the lowest variance, called the minimum variance unbiased estimator. In some cases an unbiased efficient estimator exists, which, in addition to having the lowest variance among unbiased estimators, satisfies the Krammer-Acute-Rao bound, which is an absolute lower bound on variance for statistics of a variable. Concerning such best unbiased estimators, see also Krammer-Acute-Rao bound, Gauss-Markov theorem, Layman's-Sheffer theorem, Rao-Blackwell theorem. Robustness. C.